So from now on, the session will be entirely recorded. And we are expecting to renew this workshop every year. So that you guys are the pioneers because you are the first one, but I'm expecting to renew it. But we will record it if you want to catch up later on or if you cannot follow everything. I'm going to give you a bit of theory about microscopy, but I want to be really brief about it because you just need to know a few things, and we don't want to go too deep into the theory because we can talk for hours on that. I found this video on the web, which is really cool. This is an experiment to show that light is actually two things. It's a particle, some dots, we call them photons, and it's also a wave. And the light is behaving with the two properties, and this is the experiment that shows that it behaves in the two ways. So the first one, it was throwing beads, like photons, between two slits, and you can see that they spread out outside of the slits. But it also behaves like a wave. And so if you propagate a wave through slits, they will actually diffract, interact with each other, and some places they will add them, in some places they will anneal themselves, and that's what patterns you can observe on the screen at the back. But this is an example of quantical object. Basically, what happened is that it's both a wave and a particle, like a photon. And if you do that, basically the photons can, and the wave can go through the left side or through the right side of the slit, and you have this pattern at the end. I'm gonna just replay it. And you have this pattern, and this is the experiment that shows. Can I scroll? No, I cannot scroll videos. Okay, at the end, you can see that we have a pattern that looks like, well, I cannot scroll videos and stop, so I will include the picture for next time. But this is the experiment that shows that light is both a particle and a wave, and we can use the properties of each of them to kind of do microscopy. And because it behaves like both, it's kind of hard to understand that you have actually a small dot, but it's quanta, and also you have a wave that can behave like a wave and actually behave like both. So just do two things about a wave. A wave is this kind of sign that you have here on the left. And it has two properties. The first one is the amplitude. You see that the blue one has a small amplitude, which is the distance that you have here, and the red one has a big amplitude. And the second property is actually the wavelength or the frequency. It's basically the distance between two peaks. Here in red, it's a long peak, and here in blue, you have a short peak. So now the question, now, because of there is a lot of different frequencies, we can plot them on this frequency scale. So you have very short frequency, very long frequencies, or very long wavelength, short frequencies here on the left, and you have very long wavelength, short frequencies on the right. And in the middle, you have actually what you can see, the visible light. And just to show you that we just see a very narrow portion of the electromagnetic wavelength, and it's between 400 and 700 nanometers of distance between the peak. So our eyes are kind of very, very limited in the range we can see. So now, two different questions about resolution. No, actually, that was a question I wanted to give you first. What gives light its energy? So we have two options for the wavelength. We have the amplitude or the wavelength itself. So that's my question. If you think that the amplitude is coding for the energy of the light, please raise your hand. Physically, I mean, for the people here. If you think that the wavelength code for the energy of the light, then raise your hand. Oh, okay. 5 people think that it's the wavelength, and this is the right answer. So the amplitude doesn't code for the energy of the wavelength. We have a mathematical formula calling for the energy of a light. So the energy of a light is given by the time constant, the celerity of light, which is the speed of light, and its wavelength. So it's inverse proportional to its wavelength. So the take-home message here is that the energy increases when the wavelength decreases. And the amplitude is actually coding for the intensity of the light. So more the number of photons that are going through the light, but not the energy of each photon. Okay, things are a bit mixed up, but a very important concept in microscopy, it's and that people using microscopy are mixing up most of the time. It's a resolution and magnification. These are two different things. Magnification is really the size of the object you are measuring and the image of the object, and you do a division between the two, and this gives you the magnification. The resolution is it's a distance between 2 points that you can actually discriminate. And this is a very nice example of resolution. You have this kind of double bands, and we're going to move these double bands closer and closer and closer. And at one point, you're going to see that they get very close to each other. So you can still see two pairs of bands, but at one point, they can merge. And this is the limit of resolution. So here we cannot discriminate if it's one or two bands. Here even better. So the resolution is really the minimal distance you can actually resolve to 2 points. Another very important things we're going to talk about a lot in microscopy, it's refractive index. And when I was a student, people were telling me, oh yeah, the mismatch of the refractive index. And I said to myself, okay, why is it so important? Why people just talk about refractive index all the time? But the thing is, refractive index, just to explain it very simply, is that as everybody knows, the light has a very constant speed in space or in vacuum, and this speed is very fast. It's about 300,000 kilometers per second, and we basically write it C. When light goes through a medium like a diamond, it slows down. And in diamond, it's actually very slow. It's 123,000 kilometers per second. And if you do the division between the speed in vacuum and the speed in the medium, this gives you the refractive index. So the refractive index shows you how much speed, how much light is slowing down into a medium. And then you're going to tell me some examples. So in vacuum or in air, it's about 1. In water, it slows down a bit. It's 1.33. In glass, it's 152. And in diamonds, it's actually about 2.42. So this gives you an idea of how much the medium is slowing down light. And then you're going to see, so what, Nico? We are watching light under like a few centimeters. So if it slows down, even half of the speed, it doesn't matter because we don't go far. So it's going to be a very short time length. So we don't care. Well, the thing is about refractive index is also that light, it's bent when it goes into a medium. So it's slowing down, but it's also bent. And this happens every time you change medium. So every time your refractive index change and the light goes through a surface that has a mismatch between refractive index, the light is bent. And it's about a bit more worrisome when you do microscopy. Fortunately enough, we have an equation that can give you how much is bent. And this we can calculate things and correct for this kind of behavior. So it's bad, but not as much because we can calculate it. And microscopy, you're going to use air, you're going to use water, like cells, they are in water. You're going to use also something that is oil. You're going to use glass. So there is a lot of different refractive index. And we have to calculate these things because it's going to be a mess if we don't. But then, oh yeah, this is just an example, a video that Monique Vasseur gave it to me. It's showing that glass here is actually having an impact on the laser light, and it can bend the light, but also the shape of the lens is able to do something different. So here we have a converging lens. Here another converging lens. If you have flat surfaces, then there is, in this case, diffraction inside, but a refraction at the outside. And you can have also diverging lens. So we can use this property to our advantage because we can calculate how much it's going to move. The thing is get a bit more complex. It's the bend of the light. change depending of this wavelength. And this is kind of what's happening in a prism. If you shine white light, which is a combination of all the light, all the wavelength, is going to be bent by refraction. But this bending is different based on the wavelength. So you see the red is less bent than the blue and the violet. So this is a bit worrisome in microscopy because we are using a lot of different wavelengths. We are also using white light. So this can have a bit of a trouble, and we have to take this in account. Just to show you also that light is not only a wave, it's also a particle. And when it behaves like a particle, we call it a quantum. And it's basically you have one or you don't. And this is very easy to understand, and we really like it, and we take benefit of it because it's basically 0, 1, or a multiple of 1. So it cannot be 0.5 or 1.22. The bad thing about photon, it doesn't have any mass. So it's hard to understand that something moves, but something that doesn't have a weight. And the last thing I want to say is that even if it doesn't have a weight, it moves so fast that it can actually interact and push matters. So if you put small beads and you shine a very strong light on these very, very small beads, you can actually trap this light. And this is what we use in optical trap. So even if it doesn't have a mass, we can actually interact with matters. And I'm gonna not give an example of that, but this is what happened in optical trap and optical tweezers. Another important thing, I'm gonna come back on that later, it's numerical aperture. And people talk about numerical aperture all the time. And it's very, very important. It's more important than the magnification. Yeah, but why? Well, actually, if you think about the history about numerical aperture, it's actually funny because it's a guy, Ernst Abbe, who decided to define numerical aperture by the multiplication of the refractive index and the sinus of an angle. And he just decided by himself. He didn't ask anyone to say, oh, I'm going to give this definition. And why he did that is because actually this calculation is so useful that we're going to reuse all the time. So it was kind of a shortcut to use NA and show you what NA means. The N I told you about the refractive index, so we'll reuse it here. The alpha is basically the angle between the sample that is here and the cone of light that goes into the microscope. So if you have a very narrow cone, the alpha is going to be small, so the aperture is going to be small. If you go to this NA, the alpha is going to be large, 60 degrees, and the NA is going to be 0.87. Okay, but why is this important? Well, the other example I wanted to show is that NA increase also when you have your refractive index that increase. So people sometimes tells you, oh, you are using an air objective, but oil objective is better. Yeah, but this is the reason why it's better. It's because the oil increased the NA. And this is the example why is it better to have a high NA and a high refractive index. If you have a specimen and the light goes through the cover glass here, between the glass and the air is going to be refracted, and you see that some of the light is going to be reflected. So only a small portion of the light is going to get into your lens. If you put water or oil, which has a higher refractive index, you get more light that goes into the microscope because there is less reflection and the refraction is also reduced. So you have more light. So high NA is better, high refractive index is better. And what is really important is the match between the refractive index. If you have something that is matching all the way along, the light is going to go straight. So why is NA important? Well, I'm going to get to that in a second. The second thing that is important is that if you, and to explain why NA is important, I need to explain a bit of that. If you take a single point, really a tiny, tiny point, and you put it through a lens, what you're going to get is not a point. It's going to be a blurry image. And this blurry image is called the point spread function or the airy disk. It's basically the same thing. The spread function is basically how you take from a point to an airy disk. And the airy disks look like that. And why does it look like that? It's because the light behaves like a wave. And the light interacts, they add up here in the middle. and they annihilate each other when you get into the draw here, and then they go interact again. So instead of a point, you have a kind of a function, but it's very weird and looks like that, where you have a high intensity in the middle, but then it goes down and then goes back up, and that's how light interacts with itself. So if you have one single point, okay, doesn't really matter. You can know, I have a point, and now this is the center of my point, so I know that my image is here. But if you have multiple points at the same time, well, things get a bit, fuzzy. You can have 2 points next to each other, and you can resolve them, but then they can be very close, and then it's going to be hard to, know what is resolved and what is not resolved. I'm going to go back to the NA in a second, because the question here is why NA is important. And to explain that, I need to give a bit of mathematics. And this is, again, same guy, Ernest Abbe, that defined what is the resolution of a microscope, both laterally and vertically. And in this equation, and I don't go into the detail, but the resolution is basically the distance between 2 points that you can discriminate or not. And this depends only of the wavelength and the numerical aperture. So if you have a high wavelength, D is going to increase. And when D is increasing, you basically lose resolution power. So we all want a very small D. As long as D is small, we can resolve things in more details. And the good thing about NA is when NA is increasing, then the resolution is decreasing. And that's why NA is so important. There is 2 things important for resolution. One is the wavelength of the light you're using, and the other one is the NA. And that's why I want you guys know about numerical aperture. In the Z direction, which is not represented here, it's different, and the equation is different, but the concept is the same. Lambda, the wavelength of emission, and numerical aperture are important. So the question is now, when can we discriminate? What is the value here that tells me, okay, now I can see 2 peaks, or I can see only 1 peak? And surprisingly enough, it's not Ernest Abbe who decided that. It's another guy called John Strutt, and he was a lord, and he was Lord Rayleigh, and he made this criteria, and he said, when I have 2 peaks next to each other, if the highest of the second peak is within the draw of the first peak, then I can discriminate both of them. And he could have decided something else, but he decided this, and it just happened that this distance here is 1.22. So that's why he modified the Ernest Abbe equation to give this Rayleigh criteria, which is basically how can I resolve using lambda and numerical aperture. And if we take the example of UV light, for example, and 1.4 objective, which is kind of the standard maximal we can find, this gives you a resolution of 1.74 nanometers. What does it mean? It means with a microscope, you can discriminate 2 points as long as they are 1.74 nanometers apart, and as long as you have a 1.4 NA objective, and that you are using UV light. In the Z-axis, it's a bit more because the equation is different. It's 800 nanometers for the same parameters. So you can see that it's much harder to discriminate 2 points that are close to each other in Z, whereas it's easier to discriminate them when they are in X and Y. So the take-home message is NA is important because it defines what is resolution. And the resolution is better when you are using a shorter wavelength and when you are using higher NA. So that's all you need to remember about all this 15 minutes talk. No, I'm kidding.
You give the example of UV light, but if it's, you typically work with green light, for example, or red light. So the resolution in most standard conditions would be more something like half a micron.
It's usually 250 microns for light. So this is a theoretical things that we never achieve physically. I'm going to go later in a bit more details to show. No, maybe I didn't include this slide, but yeah, this is not the resolution you will obtain with an optical microscope. It's theoretical, and you cannot expect to have better than that. But there is techniques to kind of improve the resolution that you obtain with a regular microscope, and this is called super resolution. And in the second part of the session, I will discuss that. But yeah, don't expect that you're going to be able to reach that unless you are a really, really, really good microscope. The conclusion for the first part is that light is a particle and a wave, and it behaves like both of them. It behaves like a wave because it has an amplitude and it has a wavelength. Wavelength is important for the energy, and amplitude is important for the intensity of the light. It behaves like a particle. We call them photons. They have no mass, but they carry energy with them. And this energy is based on the quanta. So it's 1, 2, 3, 4, but it cannot be 2.5. This is the equation of light. This is important to know that light is inverse proportional to the wavelength. So if wavelengths increase, the energy carried by each photon decrease. So if you go to the far red, it's less energetic than UV. Intensity depends on the amplitude. Matters slow down light. Refractive index at this equation, and it's based basically on how much matter slows down the light. Light is deviated by matters, and this is called this is based on the index of refraction. This deviation also depends on the wavelength, which is a bit of a hassle in microscopy. The image of a point is not a point, it's an airy disk. And I show you that there is a function that brings this point to an airy disk, and it's mathematical function, so it's easy to kind of go back and forth from them. And then I gave you the equation for resolution. But the take-home message is really that resolution is better with shorter wavelength and higher NA. And I gave you what is NA. So if you have any question now, please go ahead. No question? Remember the second slide? This workshop is for you. If you make it interactive, it will better answer your needs. No question? Then we move on to the second part. Oui.
On vient plus en prenant l'ouverture de l'objectif, tu vas avoir plus de lumière.
Oui.
Mais aussi, tu vas réduire ton fond de vision.
Oui.
Ça implique aussi
c'est oui.
On va utiliser des longues d'onde, pas forcément la lumière.
Qu'est-ce que j'ai pas...
La lumière, normalement, on parle d'une fluorescence des longues d'onde
spécifiques.
Donc, si on prend l'exemple de microscopie confocale,
oui.
On va utiliser le laser.
Oui.
Donc, ça s'implique aussi donc, cette approche. Donc, bien plus important que l'ouverture, moins plus réduite de le fond.
Le calcul pour la résolution est différent pour la microscopie confocale parce qu'on va réduire le champ de vision, on va réduire le airy disk. Donc, je pourrais, on va en parler tout à l'heure quand on va en parler de microscopie confocale. Je ne vais pas donner l'équation en tant que telle, mais c'est quelque chose qu'on peut aussi mesurer en microscopie. On a des slides avec des petits beads dessus et on peut mesurer combien une bead ressemble à un airy disk. On appelle ça le point spread function. C'est mieux de le mesurer que de le calculer parce que ça prend en compte vraiment le microscope que l'on utilise. Je ne sais pas si ça répond à ta question. Des questions dans le... in many cases, I have seen that the focal plane at 405 is different from 647 in the z-axis. Is this due to different refraction of both lights? Yes, the answer is, and totally yes. Because these wavelengths go through a glass, the objective, they are refracted at different angle. You obtain your focus with a 4 or 5 light differently than at 647 light. But this is not because of the 4 or 5 of the 647. Yeah, it could be because of the excitation light, the light that goes down to the objective. It's focusing at different point within the sample, but also on the way back, it's the light that is emitted by the sample is going to focus differently on the after the objective. So it's true, but because of 2 reasons: the excitation light and the emission light. And there is objectives that are corrected for that, and I'm going to show details later on. Confocal and visible in both high and low magnification. There is some chromatic aberration. Yeah, chromatic aberration are what we are talking about. Is basically that a lens is going to focus light at different distance based on the wavelength is being used. So if you compare a blue light going from a lens and a red light going from a lens, they're going to focus at different points. So, and this is called chromatic aberration, but we have good guys that can calculate it in advance and correct for that.
How do you correct?
This is the part on objective. I'm not planning to go on these details, but yeah, I can explain how we correct that a bit later. On va aller dans la partie deuxième. Tac. Second part, it's about the methods. So I tried to give you the key information about microscopy, which is NA, refractive index, resolution, properties of light, wavelength, and this kind of thing. So I'm assuming that now you are expert in theoretical microscopy. So now I'm going to go to just give you a brief overview of the methods we can apply for microscopy. The very important thing is that there is different methods, but they better fit specific applications. So you cannot use one method for all. Each method is gonna aim to a specific benefit. And microscopy is always about a compromise between speed, resolution, and sensitivity. And and sometimes people add up the convenience of use, like how easy is it to use. So if you do a radar plot with this, it's always a compromise, and you can find methods that are better in speed, other methods that are better in resolution. But if they are better in resolution, usually they are have a lower speed. So it's always a compromise. So choose your method for your specific need and for the question you're using. So about these methods, I'm gonna just give you an overview of what kind of methods we can talk about. I'm gonna really go briefly on this, but I'm going to come back to each point to give you the basic of that and also why it could be useful. So the first thing is called wide field microscopy. It's basically you shine light through an objective, you put a camera on the other side, and you catch the light. The second type of microscopy, it's confocal microscopy. And the very big difference, instead of looking at the full field, you're going to look at one single point each time. So you're going to move this point very rapidly, and that's why we call it point scanning confocal. And a variation of that is actually, instead of looking at one point at each time, you can actually put several points at the same time and move them. And this is used in spinning disk confocal microscopy. And there is a very large field of microscopy that has appeared, I would say, more recently, but it's not so much recent anymore. It's called super resolution microscopy. So if you remember, if you keep in mind the array disk I show you, you know, the big function, and if you can narrow down this guy, if you can kind of compress it, this is what super resolution microscopy try to do. And there is compromise by doing this, and there is different methods to kind of go further than the array disk. And this is called, for example, Palmer storm or localization microscopy. Expansion microscopy is not really a super resolution microscopy technique. It gives you super resolution result, but it's not at the same kind of, it's not a microscopy technique per se. There is also a variation of confocal spinning leads confocal that can be a bit super resolution. The first one was STED. The real optical method for super resolution was STED, and there is a SIM. I can explain what the acronyms are, but I think for you it doesn't really matter. You're gonna call them SEM and STEAM and SIM and PALM and STORM, and that's totally okay with that. There is also a specialized microscopy. And I think today I'm just going to have time to talk briefly about the turf and the multiphotonic microscopy. And that will give you a broad overview of what techniques can be used in the microscopy. So the first one, and I'm going to spend a bit of time on this because if you understand the concept that are in the wide field microscopy, it's going to be much better and easier to understand the concept that goes after that into a more complex confocal microscopy or super resolution microscopy. So in the wide field microscopy, there is different techniques, and basically there is two of them. One is called transmitted light. You're gonna shine light that's gonna go through your sample and get to the camera. But there is also fluorescence microscopy, and this is a different path that I will describe. In transmitted light, there is different sub-techniques to increase the contrast, and I'm gonna present some of them because I think they are cool and they are underused because they are able to do a lot of things. Then I'm gonna talk about fluorescence microscopy. It was typically called reflected light, but it's not reflected. If you look at what reflection is, this is not reflected. So I'm gonna call it fluorescence. If you disagree with that, please let me know. We can have a full discussion on that. I'm going to take a very simple example of transmitted light microscope. This is an upright microscope because the objective is at the top and the specimen is at the bottom. So you have a camera at the top that is able to digitize what you are looking at. Usually there is a lens in front of the camera to be able to focus the light on the camera. You have also a light path selector to switch between your eyepieces and the camera. You have the objective. This objective or the stage can move up and down. Why you want to do that is because you want to focus the light on your specimen and focus the objective on the specimen. And then at the bottom, you have a light source that you can regulate in intensity. This is really oversimplified, but just to give you a broad idea, what do you need? You need a light source, you need optics, well, you need a sample, you need optics, and you need a detector. In reality, we have some filters that are present in transmitted light microscopy that are diffusion filter to hide the bulb. We have also a neutral color balance filter, but I won't, all the details because I think for you they are not useful for now. But one thing that is important is the condenser that is below the stage. And most of the time, people doing transmitted light microscopy, they just don't use the condenser because they think it's not useful or because they don't know how to use it. So I'm going to focus on this little part and just show you what is a condenser made of and why you should use it and how you should use it. So we are within this the cartoon here. Can you see my cursor? Okay. No. Oh, now you can see it. So I'm going to focus on this cartoon here, and I'm going to focus on this condenser. So the condenser is basically something that's going to condensate the light into the focal plane of the microscope. So it's made of a condenser turret, which has filters. In this case, it has no filter. It has an aperture diaphragm that you can open or close, and it has a lens that you can move up and down. Again, it's oversimplified because actually there is two lenses in a condenser, but you don't need to know. The lens can be moved in and out. When you're doing a bright field microscopy, it's better to put it in so you can focus on the light on your sample. So the condenser, what does it do? It just condensates the light on the sample, and it has to be adjusted, and also mostly in Z. There is two diaphragms. One is called the field diaphragm, and the other one is called the aperture diaphragm. And you have to kind of adjust both of them to give you best results. I'm going to show you why in a minute. But basically, the field diaphragm is changing the diameter of what is illuminated by your light, whereas the aperture diaphragm change the contrast, the resolution, and the depth of field. And this is important because you want to play with that when you have a sample. This is an example of the same sample, one with the aperture diaphragm closed and one with the aperture diaphragm open. So you can clearly change the result of what you are looking at just by closing and opening this diaphragm. And I said that it was resolution, depth of field, and brightness, and contrast. So if you close it, you have more contrast, but you have less light. You have a higher field of view, but you have less resolution. So this is a compromise that you have to find when you close the diaphragm. If you open it, you have just the opposite result, and this is the image. So playing with the aperture diaphragm can help you to kind of find or see the result you want to see in your image. So this technique is called bright field, ou fond clair en français. And basically, what you just need to change on your microscope is these yellow things here. So you have to open the light source. You have to open and close your field diaphragm to just illuminate your sample. You have to put no filters in the condenser turret. You have to open and close your aperture diaphragm to change the resolution and the contrast. And you have to put the condenser lens in and to adjust it in Z. And this full adjustment is called the color adjustment or the color illumination. And there is a little part in the third part of the talk that explain to you step by step how to adjust that. In reality, in a microscope, it's broader than that. There is more components. For the microscope at the Faculty of Medicine, I make this diagram so you can go step by step and play with the things. There is shutters, for example, that are in place. Sometimes there is additional filters or polarizers that are in place. Sometimes you have two light path selectors. So things are a bit oversimplifying in the schematic, but when you go to a microscope such as the one in biochemistry, you have this documentation, and it's going to help you to kind of go step by step through the light path. The second technique I want to present is called dark field. It's an underused technique, but it's very powerful. And I'm just going to show you a brief video how it works. So it helps increasing the contrast of an image. So in bright field, you just see the light, but it's transmitted through the sample. But sometimes you can miss things that are transparent. So here we have a kind of basic microscope with a light source and a detector. You have some optics, and we're going to put a kind of a ring in the between. This ring is usually in the condenser. When you put this ring, what happens is that the light that is emitted is going to miss the objective. You see that no light is getting into the objective. When you put your sample, some of the light is going to be modified, and this light will actually reach the detector. And that's what you see. You have a black background because most of the light is out, but the sample appears into the screen. So the dark field microscopy is just keeping the light that is modified by the sample. And with this, you can actually observe things that are invisible with a regular light. So what you need to do dark field on a microscope? Well, you just need to put a filter in. And in the condenser turret, we usually have this filter. You just put it in and you have a dark field microscope. Why is it useful? Because it's very easy to use. You just put a filter in and then you're done. It's very sensitive. It gives you bright very dark image around, but you can see your sample quite clearly, and it has a very good resolution. It works very well with low magnification microscope. And what I really like is that you can see a lot of things, particularly dust and things that are unwanted. So you usually don't have a very clear image like that, but at least you see almost everything. If there is limitation, you need a very strong light because you lose most of it. So if you want to have something that goes to your camera, you need to put a lot of light. And you have a very little light that is received. So most of the time, you also need a kind of sensitive camera. It doesn't work very well with samples. And it's better to use a condenser that has a high Na. You see, Na is back again. higher than the objective. If you do that, then you're gonna have good results. And it's very sensitive to dust and floating debris into your sample.
Can you give an example of this type of sample that you typically visualize with this, like in biology labs? Not brain slices or tissue slices?
No,
cells, more?
It's usually transparent samples like cells in culture, bacteria, work with dark field, and everything that is small and that you will miss because it's transparent. But in my usage, it's just underused. I don't see anyone using it. So that's a good idea, but I should find examples or practical example to include, saying, okay, we can and we should use it with that. I'm gonna write it down. Good. Any question in the Zoom? Oh yeah, oh yeah. Nanoparticles, we can visualize with dark field. Oh, and Prio is saying that he's using a lot of dark field. Thank you, then you're gonna be my demonstrator for next time. And he used it for unstained brain sections, and it works great. Thank you for backing me up. The next technique I want to show, it's phase contrast. This is really used by people doing bacteria, and it's the same principle than dark field. And there is another great video to show you how it works. There's a slight difference. In this case, in a phase contrast microscope, we're going to use the phase of the light. So it's a wavelength, but it also has a phase. It has a phase. And we're going to use the phase of the light to kind of bring contrast. So we're going to put a ring at the top. And usually we put a second ring also inside the objective. And this second ring is here. And it's only the light that is kind of modified by the sample that goes through the second ring. This light is going to interact with each other. They interferes because the sample has slowed down some of the light. And that's how the contrast is made. It's because there is interference of the phase of the light. And to give you an example, what the phase contrast look like, here on the left, you have a bright field from Claire cell. If you put the two rings in the middle, you have this phase contrast image. So you see that here it's very dark in the middle. You see also that there is a little halo that is brighter around. So it's kind of easier to see. There is more contrast to see transparent cells. So on the microscope, how does it work? It's actually quite easy, but there is a small, subtle thing. The first thing is you need this ring that is usually in the condenser turret. It's called pH1, pH2, or pH3 for phase contrast 1. The difference between the three is that they have different size. And this size has to match the one of the objective. So you need specific objective that are called phase contrast objective. So if you use a 10x or 0.3 air objective, it has a pH1 ring. You should put the pH1 ring in the condenser turret. So it's very easy to use. You do your bright field image, you put your correct objective, and you put your phase contrast ring, and that's how you observe phase contrast images. The benefit is it works very well for cells in culture, and things that are very thin and transparent, like cells and bacteria, it increases the contrast dramatically. The limitation is that you have a halo around your cells. So as soon as you want to have to do analysis on this, it's kind of a bit harder because of this halo. Also, there is a ring within the objective. So, and this kind of decrease the resolution or the properties of the objective. So if you're doing fluorescence just after that, it won't be as good as an objective that is not having this ring inside.
If you do the fluorescence, you do the same objective.
Yeah. So to come back to transmitted light and wide field microscopy. So we are in a wide field microscopy. We saw transmitted light, bright field, dark field, and phase contrast. Now we're gonna go into two different sections here to close the transmitted light path. And it's called polarized light and differential interference contrast. And there, another video from toutetquantique.fr. And the difference between before and now is that now we really use the properties of polarization of light. and that's why it's important. So same thing, light source optics detector. Same thing than before. This is the screen showing the detector. Now we're going to put a filter that's going to select the light that is polarized in one direction only. So from a circular polarization, you have a vertical polarization. We're going to put a second filter at the end, and then we're going to rotate it so it blocks all the light. So we don't see anything. It's all black. Now we're going to put the sample in the between. And if your sample is changing the polarization of light, then you will see something on the screen. So basically, you see that the sample is changing the polarization, and some of the light is going through, and this is what you see on your screen. So this brings you to polarization. You see that the wave that is at the beginning is really round. It's because we have no polarization of light, or it's polarized in all directions. And the polarizer that is here, it polarizes the light only in one direction. In this case, it's just showing you that if you increase the size, you're going to change the color. Or if you actually rotate the sample, you have the same thing. It can change the color because you can change the wavelength, the length of the wavelength. So how does it work on the microscope? Well, and this time you still have your condenser, but it's empty. So you don't put anything inside. At the beginning, you need to put the polarizer. So it's in, and usually you have to rotate it. So it's anti-phase with the analyzer. To do that, you put an analyzer, and this analyzer is usually above the objective or after the sample. Some people actually place it directly on the slide and they rotate it. So this is a very cheap way to do polarized light microscopy. So you put these two things, and what you have as a result, it's you have bright field images, and polarized light give you colors of things that are changing, or but things that have changing the polarization of light. So the main benefits is it works with birefringent and samples. Birefringent means that you actually change the polarization of light. You don't change only the light or modify the light, but you change the polarization of light. You don't see any dust in there because usually dust is not birefringent, and it gives you a very good resolution. And you can actually change the color by changing the sample position. The limitation is that it is limited to birefringent samples. So in biology, we have some birefringent samples, such as collagen. There is some also muscle fibers that you can actually visualize with that. It's usually things that have a frequency or very thin stripes that gives you these things, this birefringent sample. Or minerals, also stones, are usually used for polarized light microscopy. Just to give you a comparison between bright field here, dark field, phase contrast, and polarized light. Depending on your sample, you can actually combine all of these methods, and you can choose the one that gives you the best result to do the analysis you want. If you want to look at your sample or count the number of debris or of stones here, you can actually use dark field, might work better. I think this is actually crystal of urea that you can find in your urine. And if you dry it up, it gives you this kind of sample. I didn't make this picture. I found it on the web. Another way of, yep, a question.
On peut quand même facilement discuter avec un microscope de base, c'est sûr que ça ne demande pas des gros ajouts d'équipement importants.
Non, c'est ça. Avec tous les microscopes de base, on peut utiliser ces techniques-là. Ça nécessite ici un filtre, ici un filtre et un objectif, et ici deux polariseurs. Donc, c'est vraiment très facile à utiliser et c'est abordable. Et on peut le faire soi-même aussi, sauf pour l'objectif phase contrast. This is an example of a piece of tissue. It's really a regular tissue, like Kim wipes. I don't want to make an advertisement for a brand. But if you look under bright field with a black and white camera, it looks like that. You can actually switch to dark field and you will see that. you see that some of the parts here look brighter in dark field because they modify the light more than the other fibers. So in this case, you can choose what is best. If you look under phase contrast, you have this halo effect around your fibers. And if you look at under polarized light, you see that all the fibers becomes white, and where there is no tissue, then there is no fiber, you don't see anything. So again, comparison of the technique can give you an idea depending on what you want to achieve at the end. The last one is a bit more complex. It's called differential interference contrast microscopy. It has more parts, and I want to go into a bit of details just to explain how it works. You start exactly the same way than polarized light. So you have here unpolarized light that goes inside. Then you put a polarizer, it becomes horizontally polarized. Then you put a prism, actually two prisms stuck to each other. And what this prism does is actually cut the polarized light into two different polarized light. So if you have a 45-degree angle polarized, something that is kind of like that, it's going to divide it into two components. One is vertical and one is horizontal. And this two component is going to be equal because it's 45 degrees. If you put it at 0 degrees, it will all go into one single side. But because we put it at 45, we have actually two beams of light. These two beams go, one at 0 degree and one at 90 degrees. You cannot see them. You don't see two beams. You just see one beam on the microscope, but there is two. If you go through the condenser, they go to your sample. The sample is going to interact with one of them, and it's going to delay the phase of one of them. So it's going to kind of slow down one of them. This is going to go into the back of the objective lens, and you put another prism at the top. And this prism is actually recombining both 0 and 90 degrees. But because now there is a change here, this is going to interfere. Because one is slowed down, it's going to interfere, and the light won't be exactly the same that you have at the beginning. And after that, you put another polarizer to remove all the light that has been not modified by the sample, and you keep only the light that is modified by the sample. So in this process, we use one light, we make it one way, and we remove at the end everything that hasn't moved. And in between, we split the beam in two, and we keep only the beam that has been kind of modified by the sample. On the microscope, what does it involve? It involves the same thing than the polarized light. So you have a polarizer, you have your analyzer at the top, and in the middle, you're going to add two prisms. One is the AC Wollaston prism that is in the condenser turret, and the other one is just above the objective. Sometimes these two are together, or sometimes these two are together. So in some microscope, it's kind of simpler. So what does it give you? Well, a lot of benefits. So it's a bit more complex, but you have a lot of more results. It's very well suited for transparent samples. You don't need a specific objective with a phase ring. It works also with a thicker sample. You have a very good resolution, especially in the z-axis. And it gives you a kind of a 3D shape. You see that you have a shadow here and a brightness here because of the angle of the polarized light that goes inside. This kind of gives you a 3D shape of your sample, and it's really appreciable when you want to show pictures. And you see that there is no halo around. There is also no dust or things that appear. So it gives you very clear images with a lot of contrast inside. The limitation is kind of a bit more complex to use because you need a polarizer, analyzer, and two prisms. And you have to adjust the prism in relation to each other to change kind of the brightness and the shadows that are here. So yeah, that's the example of bright field. How does it look? Well, I show you the comparison for the transmitted light before. You have the same cell here in bright field, and the phase contrast, and in the AC. You see that you don't have the halo effect. It's kind of way clearer on the cell, and you can see the details. And the very interesting thing about the IC is that you can combine it very quickly with fluorescence. You can overlap things. So you can have an overall view of your cells, and on the top of that, you're going to add the fluorescence. In this case, you see that you have fluorescence in the periphery of the nuclei. So yeah, very interesting technique. Just to refresh your mind on the resolution, this is the most important thing in microscopy, in my view. We have this equation, the Ernest-Abbé equation, and then we have this Rayleigh criterion that kind of refine this equation. So the distance between two differentiable points is 1.22 lambda. In the case of transmitted light, lambda is it's a mix of different wavelengths. So we take the average of 550 nanometers as an example. And then at the bottom, you have to add the objective lens and the condenser lens numerical aperture. So this is a big difference between a fluorescence and transmitted light. Here we have the NA of both the condenser and the objective. And you can buy a condenser lens with a high NA. It goes to 0.9 and can even go a bit above. So depending on the microscope, just pay attention. If you want to have a good resolution, use a high NA condenser and high NA objective. And the reminder is that you have a better resolution if D is small, so you want high NA and small wavelength. I think this is the end for wide field microscopy. We saw all of that. Congratulations, you passed. Any question about transmitted light before we go to reflected light? Who has done transmitted light microscopy? Do you know which technique you used? Bright field. Bright field. And what do you look at, and what kind of sample do you look at? Bacteria? And you don't use phase contrast for bacteria? Usually it's very appreciated in the bacteria world because it's simple.
Our lab is fairly new microscopy, so we don't have a lot of expertise yet. So we're trying to do a very basic thing, and we're not very good at it. We're working on it.
Well, you learn as you do, by the mistakes, and I've done a lot of mistakes. Okay, so then we can move to the fluorescence. Anyone has done fluorescence microscopy here? Yeah, that's good, that's good. And on in Zoom, anyone has done fluorescence microscopy ever? Yes. Oh, yeah, okay. That's a lot of people saying yes. Okay, and there is Eric who raised his hand, but I guess he wanted to say yes. So why do you do fluorescence microscopy and why it's so popular? There's a lot of people, they do fluorescence microscopy, they don't even do a bright field or transmitted light microscopy, and that's just fine too. It's popular because first, there is fluorescence molecule. So it can be things we have made ourselves, but there is also a lot of samples that are fluorescent by itself. So you don't need to do anything, it's just fluorescent. The benefit of fluorescence is that you have a very high contrast. Similarly to what you have in dark field, where you lose all the light that is not coming from the sample, in fluorescence, you see only the light that is emitted by the sample. And also in fluorescence, it can be very, very specific. You can put actually the fluorescence into a specific protein or into a subregion of a cellule. Or in these examples, you can see that you have actually filaments that are stained. You can also have animals that are fully fluorescent. So it's compatible with living animals. The good thing is also quantitative. It's very easy to quantify the amount of light you get. And this gives you a proxy for measuring the quantity of molecule you get at a specific position. One other thing that I think is important is that fluorescence can be combined into a multidimensional image. Here I put only one single color image, but you have a lot of different colors and you can separate them and combine them. So you can actually increase the number of dimensions. So it's not about X, Y, and Z now, and intensity. You can have multiple different intensity that you look at. There is a lot of different fluorescent probes you can use. So how does it work? How does cells generate fluorescence? Well, it goes about energy and light. So the principle of fluorescence is basically you shine light on something, and this something is going to respond by emitting another light. This is the principle of of the fluorescence. If you look at the molecular level, how does it work? It's basically you have a photon that is going to come into a molecule. It's going to attack the molecule and shift an electron to a higher orbital level. So you basically give energy from a photon to an electron. When this electron goes back to his resting state, it will emit another photon. Because energy is conserved, you can actually measure that, and this is how fluorescence is made. So you give one photon, and you get another photon. Because there is some energy loss, there is a difference between the absorbed photon and the emitted photon. So there is a change in wavelength. The energy is different, so the color or the wavelength is different. And this is called the Stokes shift. And the Stokes mean it's the name of the guy who discovered there is a shift. So this is the case of DAPI. DAPI absorb at 350 or 360 nanometers. It absorbs the light, it absorbs photons, it gets excited, and it's going to emit at 470, 460. This difference is the Stokes shift. And you see that you have a lot of nanometers in the between to kind of separate the absorption from the emission. One question from Marilyn. La partie quantitative de la fluorescence peut être assez critiquée car l'intensité de la fluorescence peut dépendre du temps d'excitation. Qu'est-ce que j'en pense? Je suis d'accord. Le temps d'excitation, if I translate the question, quantitative fluorescence microscopy is dependent on the intensity of fluorescence that you send, like excitation time. So if we go here, if we go to the slide before, Marilyn is saying that if you want to measure quantitatively how many photons are emitted, you need to know precisely how many photons are getting in. And this is totally right. And I agree with you. I don't know if you ask more questions on that. Okay,
Est-ce que vous
so there is a loss of energy because as you remember, the energy of light is based on the wavelength. If you have a higher wavelength, you have less energy. So you're losing energy from the left side to the right side. So where's the energy going? I said energy is always conserved. I will have to go into more details. I don't want to go into the details, but I'm just going to give you an overview because for me, it was really puzzling. Where is the energy going? So this is the ground state of an electron of a certain molecule. If I provide energy there, the photon is going to be absorbed and it's going to transmit its energy to an electron that's going to move to a higher energical state. So it can be, for example. And then the electron is going to release some energy. It can go down within the same state. It can actually go down to many different states. It can also go down to this state. And this is a loss of energy that is not related to photon emission. So we lose energy by these forward arrows. When it reaches the first level of the ground state, it can emit a photon when it goes down to the zero state. So we send this energy in, we get this energy out, and this is where we lose energy, all the purple and the orange. I don't know why I was focused on that, but for me, it was really puzzling. Where is the energy going? Usually this energy is actually heat within the atoms. There are several parameters that are very important from fluorescence microscopy. The first one is coefficient d'excitation molaire, molar expansion coefficient. It's basically how many photons get absorbed by the molecule. It's noted like epsilon, and if your molecule is absorbing a lot of photons, absorbing photons easily or not. The second one is called quantum efficiency, and this is the fraction of photons that are absorbed, that are transferred into emitted photons. It is telling you how much energy you're losing. If you have one going in and one going out, then you say, okay, I have 100% quantum efficiency. If you have you need 2 photons going in and then you lose a lot of energy and you have only one going out, then you have a 50% quantum efficiency. And to make things easier, they use a calculation.
Excusez-moi.
Ah.
Il y a beaucoup de bruit dans le background. Il y a quelqu'un avec un micro ouvert.
Assiré, Patali, ton microphone est allumé, fait qu'on entend tout.
Ah, ok, ok. Si
Dehors.
vous voulez éteindre votre micro, s'il vous plaît. Sinon, je peux vous muter. Si je sais qui parle, je peux vous muter. Est-ce que le problème de micro est réglé?
Oui.
Oui,
Comme
tout
je
va
ne vous
bien.
écoute pas, je ne saurais pas. Donc, je peux écouter. C'est réglé? Parfait, merci à vous. Ah, une question de Marilyn?
Est-ce que vous m'entendez?
Oui, je vous entends.
Ah, parfait. Tout à l'heure, je crois que mon micro ne fonctionnait pas. C'est plus simple de parler que d'écrire. Par rapport à justement le temps d'excitation pour quantifier avec la fluorescence, comment on peut être certain de quantifier réellement la fluorescence de notre échantillon et non pas une trop forte exposition?
Alors, dans le chemin lumineux, il va y avoir plusieurs paramètres qui vont arriver en fluorescence pour enlever la lumière d'émission. Ce qu'il faut faire, c'est quantifier la lumière qui rentre, et ça se fait en dehors de l'échantillon. Puis après, on va mesurer la lumière qui sort, et ça se fait avec une caméra, et on va voir ça un petit peu plus en détail après.
D'accord. Et ça, c'est possible en confocal si on fait de la fluorescence?
C'est possible dans toutes les méthodes d'imagerie.
Ok, super. Bah, j'ai hâte de voir la suite. Merci.
Alors, on continue. So yeah, I talked about extinction coefficient, absorption coefficient. I talk about quantum efficiency. And to make things simpler, they just combine these two factors into brightness. So brightness equal how much photons you absorb and times how much how efficiently you transform into emission photons, and you divide by 1000. And there is another parameter, it's a lifetime of the fluorescence. So this is usually noted tau, and it's in nanoseconds. So if I excite some light, this fluorophore will take time to emit light, and this decay has a lifetime, and it's really particular of each fluorophore. And the last parameter is the photostability. It's if I shine light on a fluorophore and I wait and I shine a 500 photons per second for a period of time, I wait and I measure how much light do I get, and I want to know how long does it take to reach 50% of what I had before, and this is called the photostability in seconds. So with all these parameters, each fluorophores have all of these parameters, but are specific of them. You can actually choose the ones that are the most relevant for your application. And I built a specific exercise for that. The first one, so it's going to be an interactive. I'm going to ask you to go and do work. The first thing is to actually find the characteristic of one fluorophore you are usually using. So I'm going to take you. Do you use a fluorophore? Anyone else using a fluorophore here? Anyone using fluorescence? Okay, what fluorophore do you use?
Alexa fluor.
Alexa for
Yeah.
488 or for?
488.
Okay. Do you know what is the absorption coefficient and the quantum efficiency?
I'm not really, because it doesn't affect my work, but I can go for it.
Well, actually, you can ask yourself, why am I using this one? Is there a better one? And that's why I want you guys to have the thinking about it and to actually go and find this information, because these are really important information. And you can improve a lot your experiment by just, okay, 488 is good, but I see that Psi5 or Psi7 is better. Maybe I can just change my secondary and I'm going to improve drastically my signal. I don't have your name, but Gilles? Julien, qu'est-ce que tu utilises comme fluorescence?
FM464 et FITC.
FITC, FM464. So the ones that are in Zoom, I want you to open your favorite browser and try to find the absorption coefficient and the quantum efficiency, at least for your fluorophore. and you can type it in into the chat. I'm gonna do that for FITC. So I'm gonna go to Google, and I'm gonna type FITC quantum efficiency. Because I don't see my screen, it's gonna be, I'm gonna type it here and I'm gonna find the result and I'm gonna give it to you. So FITC, quantum efficiency. So FITC is called fluorescein. Takes a bit of time. FITC quantum efficiency is 27. So what it means is that if I receive 100 photons, the FITC is going to emit only 27 photons. So I lose a lot of light. Is FITC good? Yeah, not so much. Now the other question is, what is the absorption coefficient of the FITC? And this is, it's here. It's 78,000.
Nice. Des fois, il n'y a pas de fluorescence. Ça arrive.
Pardon? Oh, c'était peut-être pas pour moi. So FITC has a extinction coefficient of 78,000, and this gives a brightness if you multiply both of them by 77. So the second question of the talk is find a database of molecules that are listed by their absorption coefficient and quantum efficiency. So there is some database online. You can look for them and find them. And what is good is that you can actually choose what is the best for you. I have such a database, and I'm going to give you the link for that after that. But I want you to have the skill of finding, okay, actually, I need this answer. I'm going to go and find it. You can just go on Google, and you're going to find it quite easily.
Si on compare les molécules fréquemment utilisées, FITC dans l'hexoc 8, le même genre de longueur d'onde, est-ce qu'il y a une grande différence de d'efficacité quantique?
Alors, on va comparer ça. Je vais trouver le 488 parce que j'ai ma base de données. Alexa 488 has a quantum efficiency of 24/7 and absorption 71,000. So FITC is slightly better than Alexa 488. So, but I have this database here. Actually, I have a table here. But has a lot of protein, and I can sort them by brightness. And you see that the brightest thing is actually quantum dots. And then you have all these ATO reporter that are quite bright. And Alexa 546, TD tomato, it's a very, very bright protein. So if you want to do a transgenic mice, use TD tomato because it's super bright, it's in the red. So there's going to be a lot of advantages. Another thing that is present in this table is actually the stock shift between the absorption and emission. You want to know how much space do you have in the between. If they are very close to each other, it's going to be hard to find filters that match this thing. If it's broad, then it's going to be kind of easy. And you see that here you have a 27 stock shift, so it's quite easy. So yeah, this database. I'm going to give you where I found it. And the last question I wanted you to do in the exercise is to look at lifetime imaging, fluorescent lifetime imaging. So when fluorescence is, when a molecule is excited, it's going to decay. And this decay is very particular of the compound you are using. you can actually use this decay to kind of fingerprint which molecule is there. So instead of looking at the brightness, you're going to look at the brightness over very, very short time scale, microseconds, things that are very short. And this decay is going to tell you, oh, it's a GFP molecule, or it's a chili tomato molecule, or it's a FITC molecule. And it's very specific of them. And now there is a full field of microscopy that goes into these kind of details. You don't need to select a filter. You can just measure the fluorescence over time, and it tells you which molecule it is. So you don't use filters anymore. Well, actually, you still use it, but you can actually recompose which molecule is giving you the fluorescence. Yeah, so take this presentation there. So this is what I wanted you to find about fluorescent lifetime imaging. Within this database, you have this kind of information, and I'm going to give you some links about that at the end of the fluorescence session. Question?
So when you want to choose a fluid for what parameter do you really target to get the best results?
Brightness.
Brightness.
The first thing I go for personally is brightness, but then it also depends on the full experiment you want to do. If you want to do a free color experiment, you might use different things, because if you take something that has a very high brightness, but you have something next to it that has a very low brightness, you're going to have some difference between the contrast. So it's going to be difficult. So if you have a fixed variables, such as I have an animal, it's already GFP positive. So I have GFP that is fixed. I want to add something. I won't take chili tomato to go with GFP, because chili tomato is much brighter than GFP. So you don't want to do that. Otherwise, it's going to be mainly tomato and you can barely see the GFP. Also, you have to look at the wavelength specifically to kind of make sure they don't overlap between each other. Usually DAPI, that has a very broad emission spectra, is going to overlap a bit with other components. So you have to kind of be careful when you're using this kind of thing. But it's on an experiment basis. Any other question? So now a little video about fluorescence microscopy. So things are different in a fluorescence microscope, because the light doesn't come from the bottom or the top anymore. It comes from the side. And that's why we were calling them reflected light, because the light comes from here. You see, it's a multicolor light. When you put a filter, it becomes blue. And this light through a mirror goes down to your sample. Your sample is going to be excited by the blue light. It's going to emit some light, green light, but go through the objective. It's going to go through this very specific mirror, through a filter towards the camera. So people were saying light is reflected because it goes down and then it goes back up. But the reflection of light is a different thing. So this is why I call it fluorescence. So to go into more details and show you what does it look like on a microscope, this is exactly the same thing than the video. You have a light source, but usually very bright and very white. It emits in all wavelengths. It goes into something we call a filter cube. This filter cube is made of 3 components: an emission filter, a dichroic, excitation filter, dichroic, and emission filter. So we're going to select only the blue light to go down to the objective, excite the sample. The sample is going to emit some green light, always lower wavelength because of the stock shift. Goes through and it goes to the camera or to your eyepieces. If you go into more details into a filter cube, this is an important part in microscopy. Filters are written usually with a number / another number for filters that select a band. So in this one, the band is centered between 480 nanometers, and the width of this band is 40 nanometers. So it means that this filter lets light from 460 to 500. So it's 480 minus 20 and 480 plus 20. This is called a band pass filter. Then it goes down, the sample emits some light, and then you have this thing called a dichroic mirror. It's written usually with a number, which is the main wavelength, and long pass, meaning it's going to let any wavelength that is higher than this number to go through, and it's going to reflect all the light that is lower than that. So this is what I've written. All the light that is lower than 505 is going to be reflected, such as this light. So it's reflected. All the light that is higher than 505 is going to be going through. There is usually a 10 nanometers window where you have a bit of both. So that's why we put here another filter, emission filter, same thing than the excitation filter, 535, 50. It has a 50 width and it's centered on 535. So it lets 510 and until 560 nanometers wavelength go through. If you represent this into a graph where you have a wavelength here and transmission here, this is a short pass filter. You see that all the light that is shorter wavelength are going through. It's transmitted by the lens or the filter. All the light that is higher but this value here, it's blocked. You can have a long pass filter, which is basically the opposite. And you can have a band pass filter, which is kind of a combination of both, where you just have a centered and a width that is transmitted. You see that this is not perfect. You have some light that is here. There is a slope. It's not like vertical. And because there is a slope, you just have to be careful that it's not perfect. When I say it's between 460 and 500, it's actually 460, but there is still a bit of 458 and 455 that goes through. So filters are not perfect. If you go to the company that sells these filters, it's cool because they give you actually the graph, how much light it's transmitted at a particular wavelength, and you can download this thing. So this is the example for the 48840. This is the long pass filter. You see that it's a long pass. As soon as you go higher than 500, everything goes through. You also see that there is some kind of it's not perfect. There is some kind of light that still go through. There is 50% of the light at 400 nanometers that go through. So it's not perfect. And you can combine them into a set. And this is the example for the cube called 41001. So you have the emission filter, the excitation filter, the dichroic, and the emission. And not all the cubes or the set are the same. This is an example from the same company, the same cubes or the same values for the cube. You can see that there is a difference from the left side to the right side. And what's the difference? What's different between left and right? Dun, 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 dun. Well, the difference is that the transmission of light for the blue is much lower on the left side than on the right side. It means that if I shine light at 475 nanometers, only 80% is going to go through, whereas here, almost 100% is going to go through. So this is a much better filter. And it's
more expensive.
No, it's not more expensive. They actually don't make it anymore. So you cannot buy the 41001 anymore. So you can only buy this one.
But yeah, different grades, right? Filters are cheaper.
Yeah, there is basically two kinds of filters. There is a soft-coated and hard-coated. And technology is different. The hard-coated can live very, very long. The soft-coated, they just have a layer on the top. So they go bad very quickly. So yeah, but this is more of my job at the microscope to kind of choose the right filters and make sure they last long and they are the best for the application. So if we combine the two things, we have dichroic mirrors and we have it has these parameters. We also have a fluorescence spectra from the protein in here, GFP. I told you that they absorb at a wavelength and they emit another wavelength. And what we want is actually combine both. We just want to make sure that my GFP is going through my cube. And this, you need to check it before you do your experiment. Fortunately enough, the website from the company lets you do that. You can plot the GFP curve here in green, the absorption and the emission on the top of the filter set. So what you can see is that the GFP here is within this excitation filter. So we're going to excite at the wavelength where GFP is going to absorb. And you see that GFP is emitting here. And you can see that this filter is not exactly on the peak of the GFP. It's just on the side. You're still going to see some light because there is some curve here, but it's not the perfect filter for the GFP. So this is very important when you check your microscope that the fluorescence you're using is matching your filters. If it's not matching perfectly, you're gonna decrease the signal a lot. So here it would be better to have a filter that is more close to the 500, 510, and have a decorrect filter, decorrect mirror that is closer to the left. We can also do the same example with the DAPI. So DAPI has a very broad excitation, it's here, and a very, very broad emission, it's here. You can see that this filter doesn't let the excitation of the DAPI through, so because it's not overlapping. So there is no chance to see your DAPI with this kind of filter. So the good thing is you're gonna block all UV light. You can compare also with a very close to GFP, the Alexa 488. And you see that in the Alexa 48, you have the full peak that is within this band. So a lot of people think, oh, GFP, Alexa 48, FITC, it's all the same. No, they are not exactly all the same. And also the filters are not exactly all the same. So you have to kind of check before you do your experiment that these are actually matching. In this case, you see that also the excitation is a bit, you are missing the peak of the Alexa 48. So you're gonna excite a bit less your fluorophore, but you're gonna tap or get more of the light that is emitted. Excuse me. Now, a tricky question only for the best of you. This is the CubeSat 4900011, and I put GFP, Alexa 488, and FITC. And my question is, what is the best fluorophore for this cube? I asked this question to several people, and it's hard. So if you don't know the answer, it's fine. If you know the answer, please come in, and I will let you explain why. You're a new PhD student.
The FITC, because the excitation filter covers most of the absorption spectrum, the FITC, and the emission filter covers most of the emission spectrum of the FITC. While the other ones, it's partial for the excitation for the EGFP, but it's pretty good for the EGFP for the excitation, but not so good for the emission.
Yeah.
And for Alexa 48, we're missing the peak excitation, so it's not ideal.
Yeah.
That would be my suggestion.
That's totally right. But does it mean that FITC is the best for my experiment? Well, we also have to look at the absorption coefficient and the efficiency. So in total, this doesn't tell you the full answer, but the answer to this question is FITC is the best matching fluorophore for the filter. Actually, it's the opposite. The filter was made for FITC. So they kind of design it in the other way. So just to close up on the fluorescence, knowing the spectra and knowing the properties of the molecule are important. And this is things that are underlooked by most of us. Because I want to help you as much as I can, I put these resources about filters and fluorophore, especially this one, fluorescentproteinbase.org, gives you the spectra of a lot of things. I can maybe do a small demo if we have time. It's 10:41. It's the time for the break. So maybe we can take a small break. And at the same time, if you want to stay here, I'm going to try to do the demo.
Before you start, can you just go back to one question about the previous different dyes and their comparisons in the database that you mentioned before? Does that include some characteristics about the stability, the photostability? Because like this is another characteristic. I think you didn't talk so much about that. Like some are very bright but might leach faster than others. So
yeah. So this is what you can find in this database. You see that it's completely made, personally made, and you don't have the photostability that is present here. Photostability is kind of a problem because the definition is not fully agreed on. Some people think it's the time it takes for 500 photons per second to decrease 50%, but some people use 100 photons per second. And it's kind of a limited number of people are able to kind of do this measurement. So there is no unified database for that, at least that I know of. But if you find a database that contains such information, I give you an extra point to your non-credit workshop. Yeah, so the fluorescent protein database, the spectra viewer from Thermo Fisher, and also these ones that are kind of less interesting. I'm just going to check because this table comes from a lab, Daniel Côté lab in Quebec City. He put up on a website and you can actually feed in all your things. I just extracted the data and I made this table mine, but it's all of his information. And yeah, they are also made for 1 photon and 2 photon imaging because we're going to talk about multi-photon later on. So yeah, so please have a 7-minute break. And I'm going to take a break too. Oui. Il n'y a pas de problème. De toute façon, ça va être enregistré. Tu pourras le regarder et le re-regarder en famille. Il n'y a pas de problème. Ah, ok. Bah, vas-y, vite. Bye.
Salut, j'avais juste une question vite.
Vas-y, David. Je t'écoute.
Merci premièrement pour tout ça, c'est vraiment intéressant. Mais je me demandais juste pour les enregistrements, où est-ce qu'on va pouvoir les trouver à la fin de la session?
J'ai mal entendu ta question.
Ah, pardon. Je me demandais juste pour les enregistrements, où est-ce qu'on va trouver les enregistrements à la fin de la session?
Ah, aucune idée. Pour l'instant, je n'ai pas encore prévu, mais j'enverrai un courriel pour dire où est-ce que seront les enregistrements.
D'accord, merci beaucoup.
Mais ils ne seront pas sur Studium, ça je peux te le dire.
D'accord.
Juste avant la pause, on parlait de ce site fpbase.org. Et je voulais prendre un exemple pendant la pause pour vous montrer un peu de quoi il en retourne. Donc, ah oui, bien vu. Merci Monique. Qu'est-ce que je ferais sans toi? Des bêtises, sûrement. Mais partager quel écran? On va partager celui-là déjà. C'est bon? Merci. Donc, je voulais prendre l'exemple de fluorescence protein database.org, qui est vraiment un outil qui fait vraiment des choses intéressantes pour la microscopie. On a beaucoup de choses très intéressantes et je vais prendre l'exemple ici de deux protéines d'intérêt. J'ai mis le DAPI ici. Donc, on a la courbe d'absorption avec le maximum à 359 nanomètres, la courbe d'émission 457 nanomètres. Puis, on peut rajouter juste en tapant dans les fluorescentes protéines, on peut, je sais pas, on peut taper le GFP. Puis, on a la courbe d'absorption et la courbe d'émission pour le GFP. On voit que le stock shift est complètement différent pour le DAPI versus pour le GFP. Après, ce qu'on peut faire, c'est qu'on peut aller chercher des filtres spécifiques et les mettre et voir comment ils overlappent avec un spec particulier. Donc, on voit que ce filtre chroma 490-20, il est très spécifique pour la GFP. Donc, ça peut être une chose intéressante. Ah oui. And we can also look at light sources. And this is very important. I didn't talk about it, and I won't talk about it. But light sources have to match the absorption spectra of the molecule you want to excite. So this is the Excite 120Q. It's a metal halide lamp. You can see that it has peaks at specific wavelength. One is specifically good for DAPI. You're going to excite very well the DAPI if we have a good filter. But you see for the GFP, you don't have a peak here. You can still be able to excite, but it's less intense than what you're going to have for the DAPI. So be aware that the light source can be not as good for one fluorophore versus another one. If I add another fluorophore here, such as this red, you see that I have a peak here at the back for my, maybe I have too many things on the top of it over. So I'm going to remove the GFP and remove the DAPI, and I'm going to remove the DAPI. So I just keep the light sources. You see that I have a peak here for the light sources that match the peak of the fluorophore that I'm looking at, which is GS red. So this lamp is going to be very good for that, but not very good for GFP. So you have to be aware that light sources can be an issue, and this website lets you actually use that. Another thing is about detectors. This is a camera we have. You see that the camera has a sensitivity that is better at 400, 500, just about a bit less than 500, 490. And then it goes down. So the camera is going to be better for GFP, but not as good for the red. If you look at another camera, such as or the camera Evolve, which is a very good camera, you see that it's very, very good in the red, and it's much better than the Cool Snap, which is about the same age. So if we look at the Orca Flash, it's in the between. It's pretty good in the red. That's the good thing about the Orca. It has a very good definition, but I will talk about the cameras in a bit later. But this website lets you merge all of these things into one single graph. So go to this website and bookmark this, because you will have to check every time you do an experiment. Just quickly check your fluorophore, the filters you are using. And the good thing is also you can save this as a setup. You can also, and if I have time one day, I'm going to do that. You can make it for a specific microscope. So let's say someone is coming to use a microscope here. I will save the microscope. So you just have to type your proteins and you're going to see, oh, it matches or it doesn't match. So a very interesting website for that.
I have a question. Here for the overlap between the fluorophore, I mean, what is the acceptable value for the
it's a combination. So there is the question is what is acceptable as an overlap between a fluorophore and a filter. So for example, if I put here another filter, Chroma 41910, and I put the GFP here. So the question is, what is acceptable? I'm going to remove the detectors. The question is, what is going to be acceptable for the overlap between the peak that is the GFP and the peak that at the back. This is really depending of a lot of factors. The first one is the light sources. How much light is going to go within this filter? The second is how much my detector is sensitive. If I have a very sensitive detector, maybe I don't need to have a perfect match between the curve. So these things have to be kind of empirically measured, and it really depends on one system to another. Because you don't usually know all the microscope, the first approach is to come to me or to the person who is responsible of the microscope and ask him, have you ever used this? Is it working well? And they will let you know. Another thing is when usually you start using a microscope, when you know the microscope and you know that GFP works very well on this one. If one day you come and your sample doesn't work, you know that it's not because of the filters, because you have used it before. So empirically, you can determine it. The best thing is to come to us if you have a doubt and ask us, is this going to work on this specific microscope? And we will do this. And based on the camera and the light source and everything, I will tell you yes or no, it's going to work well or not. Any other question in the chat? Then I'm going to go back to display settings and extend display. Good. And then stop sharing. And then share screen again. Good. And go back to the presentation. Oops. Okay. Okay. 1 minute.